Hi there, this is Coach Suiso, and welcome to this video on 714, which is the free energy of dissolution. Before we begin, just some reminders since I'm not here today. You should be doing your Throwback Thursday or have done it already before you start these notes, so make sure that that is taken care of. After you finish these notes, you can do the We Do and then scan the QR code in the We Do to check your work on that to make sure you did it correctly. And then you'll work the You Do questions. There's only 2 of them for this lesson, and check your answers up at the front before you go home for this weekend. And then remember your homework for this weekend. Tonight, your OWL is due at 11:55. Make sure that that is finished. And then you're going to be studying for your test. On Monday, we will do multiple choice madness, free response whiteboarding, and then we test on Tuesday. All right, here we go. 714, free energy of dissolution. So what we're going to do today is explain the relationship between the solubility of a salt and the changes in the enthalpy and entropy that are going to occur in that dissolution process of that salt. So there's several factors that can have an effect on dissolution. The first is going to be our enthalpy, which we've talked a lot about, particularly in Unit 6, which is delta H. That measures your potential energy or your heat content of the reaction. Remember, energy is needed to break those solvent-solvent reactions when you dissolve something. So that would be like, say, the water to itself. Energy is going to be needed to break the solute-solute attractions, which is the salt to itself. And then energy will be released when you form those new solute-solvent attractions and put it into solution. So then overall, energy will either be released or be taken from your surroundings. Another factor that can have an effect on dissolution is our entropy, and that is going to be delta S. Entropy measures the randomness or disorder of some sort of solution or system. So your solute is going to be more ordered before dissolution, which should make sense. You have a salt and you have water, and your salt should be in crystal form. Your solvent will also be more ordered before dissolution because you have, say, pure water or whatever the solvent is. Your dissolution is going to lead to an increase in disorder, or what we call a positive delta S. And your surroundings could also increase in disorder. So one way to think about entropy is the probability of particles or energy being distributed into all the tiny places with a container, or what we call the microstate, so spreading out. I always think of entropy like the universe always wants to go towards disorder, right? Like you can clean up your room, I can clean up my classroom, my desk. By the end of the week, it's always going to be a mess, right? Because things will go towards disorder. So the entropy will generally be positive for things. So if we look at this visually, right, like salts, for example, like NaCl, they're very ordered crystal lattices. And water, because of the hydrogen bonding, is also very ordered as a liquid. So this is what it all looks like, before it's dissociated. But once I dissociate, if you look over here, look at the disorder of this, right? So there's a large increase in that disorder or that entropy, okay? So entropy in general is going to drive that dissolution. As we've seen, dissolution can be exo or endothermic, right? We tested all the salts for the hand warmer lab. Most salts generally will dissolve pretty easily, even if they are endothermic. And the reason being is because entropy is that driving force behind the dissolution, not the enthalpy, because it wants to move towards disorder, which is why even the salts that, in your hand warmer lab were endothermic and had to have energy pulled from the surroundings to dissolve, they still dissolved. I didn't have to heat it up for the most part to get it to dissolve, because it wants to go towards entropy. Temperature will also have an effect, right? Like if I'm making large portions of a salt or a solution for you guys that I'm making in a lab, I will heat it up, particularly with like NaOH and things like that, because temperature will increase my solubility. So now finally, we're going to talk about Gibbs free energy, which is delta G. This is an equation, okay? They're related. Our delta G, which is our Gibbs free energy, our entropy, which is our delta S, and our enthalpy, which is our delta H, via this equation right here, okay? We are not going to actually solve any problems with this equation until we get to Unit 9. Gibbs free energy is kind of one of the hearts of Unit 9. So we'll calculate it. We'll kind of, talk more about it and get more into depth. But for now, we're just going to use basic qualitative analysis to determine if a reaction is going to actually happen spontaneously or not. So what highlighted here is kind of the key of this. The larger the negative value for Gibbs free energy, the more the reaction will favor the products, or it will happen spontaneously in the forward direction. So there's 3 processes of dissolution, right? You have to overcome intermolecular particles between your solvent, overcome intermolecular particles between your solute, and then reform the bonds and the intermolecular forces between the solvent and the solute. So when I break apart those intermolecular forces between the solvent, my enthalpy is positive, which we know it's endothermic, and then my entropy is going to also be positive. I'm moving towards disorder. When I break up my solute, endothermic, positive, okay? Overcoming those forces. Then when I reform my intermolecular forces between my solvent and my solute, that is going to be exothermic, and it's going to have a negative entropy. So when I apply that to Gibbs, again, we're just looking at this qualitatively, not quantitatively yet. If I've got a positive H and a positive delta S, my reaction is going to proceed spontaneously at high temperatures. If I'm at low temperatures, it will be spontaneous in the reverse direction. If I have an endothermic reaction with a negative entropy, my delta G is always positive. The reaction is spontaneous in the reverse direction at all temperatures. And then if I have a negative and a positive, my delta G is always negative. The reaction is going to be spontaneous at all temperatures. And then if I have a negative and a negative, my reaction will proceed spontaneously only at low temperatures. At high temperatures, my reverse becomes spontaneous. All right, so let's look at this one together. This is the I do, and you've already gotten the answer written out below in your notebook. But it says, which solution will have a greater entropy with all other factors remaining equal, and justify your answer. So A says we have a saturated solution of cobalt hydroxide, and it's given my KSP for it, which is 5.92 times 10 to the negative 15. B says a saturated solution of beryllium hydroxide, which has a KSP of 6.92 times 10 to the negative 22. And we want to know which one's going to have a greater entropy, which one's going to move towards more disorder. Okay. So if I look at it, my two KSP values, this one has the higher KSP. Okay, so that means if I have a higher KSP, more of my ions are going to dissociate, right? And if I have more ions dissociated, I've got more ions in solution, more possible configurations for that system. I have more disorder if more is in solution. So A will have more disorder and therefore a greater entropy. Hopefully that makes sense. If you have any questions on that, let me know. You can shoot me an email. You can shoot me kind of a message on Canvas, and I will get back to you if you have any questions on it. And again, we'll go over it on Monday to make sure you understand it. Go ahead and do this You Do We review. After you've completed it, you can scan the QR code, see the answer. It's walked through very nicely with really pretty drawings that are much better than my artistic ability. And then you can work on the You Do's. Thanks for listening. Make sure you took good notes, and I'll see you guys next week.